All right. Okay. All right. So happy Valentine's Day, everyone. For those people online, happy Valentine's Day. The class sends you their love. Um, so we are going to have a wonderful lecture today. And let me see what I was thinking to remind people of. Well, we don't have a homework due tonight, so this homework is not due until Wednesday. This homework on lines. We're going to finish talking about functions and relations today. So there's a homework on that subject that I will post. And today we'll start talking about angles and how we measure the size of angles, which is sort of well known to you, but we're going to look at that very carefully because that's going to be an important skill for us going forward. Most people did okay on the ellipse homework, actually better than on the prior homework. So that's good. For some people that maybe that didn't have a score or didn't have a very good score, I sent out a reminder that as always that you can ask for an automatic extension, right, of the due date. Just make sure you do that quickly after the due date, right? So wait till after the due date and then ask for the extension. Oh gosh, there was something important I was going to say now, but it's slipping my mind. It will come to me at some point. I just as a reminder, I'm in my office after class starting I usually don't get there till about 1. So I'm in my office, which is in South 611 in the one main building on the south side in 611. So I'm in there, but I can also do Zoom during those office hours. And so, but if you're going to do, I don't always turn the Zoom on just automatically. So if you're going to come to the office hours through Zoom, you can always come and knock on the door. But if you're going to come to the office hours through Zoom, it's good to email me or remind me that you're going to do that so that I'll be so that I'll keep so I'll have the Zoom session running if you're going to come to my office hours. So that's another way to get help. And also remember you can use Ask Your Teacher, right, with each question. So don't forget you have that option of emailing me through WebAssign through that Ask Your Teacher button with each question. And that's really good because then it sends me a copy of the question. So that gives me a really good idea of what's going on. I can't always answer the question though, immediately. So sometimes we have to wait and do it in class, but sometimes I can tell you, if it's a small mistake, what it is you need to fix. So don't forget you have that option. You can use that anytime, but if it's going to be like, just shortly before the midnight that the homework is due, there's probably a good chance I won't respond to that because I'm just not going to see that message until it's too late. Okay. I mean, I will respond to it, but it may not be in time to for you to get credit for that question before the due date. Oh yeah, now I remember what I was going to say. All right, so someone had asked, actually it was Amanda, had asked about adding tries to the ellipse homework on each question, because you're limited to 5 tries. So I usually by default you're limited to 5 tries. So I did increase that to 8 for the ellipse homework, but I didn't remember that request until like Friday night. So and then I added the extra tries. So I don't know if that benefited anybody or not, but I did remember to do that, but it wasn't until it was already Friday on that Saturday homework. So I think on lines is back to 5, but I didn't check the settings for that one. Okay, those are things I want to remind you of. Do y'all have things that you want to ask in particular? Okay, all right, good. Anybody online with Anybody online with any questions? The test is supposed to be, Hannah asked this earlier, the test is supposed to be a week from Wednesday. And remember the sample test is posted, but I haven't posted the answers yet because I want to give you a chance to work on that without me showing you the answer. So it'll be a little while before I have those posted. But we'll have to see if we stay on schedule for that test on the 23rd. We may have to postpone it till the following Monday. I was mentioning I'm one day off of my normal schedule because of Martin Luther King Day. We started on Wednesday instead of Monday. So so that may throw us off. We'll have to see how far we get today. See how much progress we make today. So today we're going to finish talking about functions and relations. Then we're going to go on and talk about angle measure, which is really easy, conceptually very easy. There's only one thing that's a little bit complicated about it, and that's how we measure angles in calculus. Is slightly different than our standard way of measuring angles. What you've known since you first learned what an angle was, right? That's degree measure of angles, right? Which is most ancient way of measuring angles. That's dates from the time of the Babylonians invented that system. So, but in calculus we have to do it slightly different. But we still use degree measure, so we kind of interchange. That's the only thing that's a little bit complicated about angle measure. Okay, but I have a recall practice for you, so I mentioned that. So so let's look at that. So this is just to remind us of our definition of function. And so very easy question here. It's just which of the following relations, so each of these objects here can be thought of as a mathematical relation, which remember is just a set of ordered pairs at its using its most abstract definition, just a set of ordered pairs. And each one of these mathematical objects you can think of as a set of ordered pairs if you think about it just properly. But not all of these are functions. So which of these relations matches the definition, meets the definition of a function? So this is just a yes or no question for people to answer. Don't chat it in yet, though. Okay, we'll let's give everyone a chance to look at it, and then but be thinking about if you answer yes or if you answer no, you want to give an explanation, right? Okay, so be thinking about what your explanation would be. I'm going to pass out some graph paper to the class because we may get to do some graphing today. See how far we make it. While y'all are thinking about that. So just plot some angles today. Yeah, take a little bit. Okay, let me fold the screen back. All right, I should have set this up as a polling question. So what about that in A? What did y'all vote? Did y'all vote, is that a function or is that not a function? Okay, so the class is mostly saying not a function. What do y'all guys say online? What did y'all think? Yes or no? Muhammad says no. Fernando says yes. Oh, so we have a disagreement there. That's good. All right. Okay. All right. So We can have a debate there. Okay. All right. All right. Oh, well, Kenneth, you're already answering C, so you're a little bit ahead of us there, right? We're only talking about A right now. All right. So in the class, y'all said mostly no. Who said no there? Hannah, you said no. So why no? Oh, so you have repeating X inputs. All right. Is it -2 that's repeating? Oh, I see. So, right. So you have -2 with 4, and then you have also here -2. But look there, Hannah, that's also matched with 4, right? Okay. So I think that's what, who answered that it was a function? Was it, let me scroll up there. Was it Fernando online, I mean, that said it was a function? Fernando?
Yeah. Mhm.
Yeah, you said it was a function. So why do you not why do you not agree with Hannah's objection here?
Because it's even though it has repeating x functions,
Uh-huh.
they're still the same output.
Right, yeah, Hannah, right. Okay, so this was a trick question, Hannah. This was a dirty question. So you have you do have repeating inputs, right? Which normally, you know, 99 times out of 100, that's going to keep it from being a function. All right. So, but in this case, it was just set up to fool you because the output in both cases is the same. All right. So what you have to be careful of really is a repeating input with a different output. All right. So normally, though, you wouldn't see a situation like this because you wouldn't repeat this ordered pair. You see, okay, right? That wouldn't be necessary to repeat that ordered pair. So yeah. All right. So technically, it is a function, but it was kind of set up to make it look like it was not a function. So actually, both of you were right. Okay. All right. So what about B? Think about that one for a moment, or did you already think about that one? Okay. So what do we say up to B? Not a function. Fernando, what did you say to B?
Not a
Online,
function.
Fernando. Huh?
Not a function.
Not a function. Okay, so Fernando, what's the difference there between what's the difference between this situation where we had repeating inputs and this one in B?
It has the repeating x inputs have different outputs.
Yeah, can you show me one for example here?
2 would be
2.
2 and 0 and 2 and 5.
Yeah, okay, right. So 2 is an example of one, right? I thought you would pick a more obvious one like 4, but 2, right? That input has 2 different, if I can draw it right here, that input has 2 different matching outputs, correct? Because 2 is matched with x value 2, right? Is matched with the y value 0, because this point is on the graph, right? I think. And then also up here, there's a second point that has x coordinate 2. It's a little bit above 5, right? Okay. So you said 5, but it's actually slightly above 5, but I don't know what it is there, right? Okay. Something like 5.4 or something, but we don't, it doesn't really matter, right? Okay. Exactly what that y value is, there is one, right? So the input 2, for instance, has 2 different matching outputs. So that keeps this from being a function. So whenever you see a graph like this where it has loops in it like this, okay, not going to be a function, because if you've got loops in the graph, you're going to have situations where the same input has more than one output. Okay, lots of loops here, so there's lots of opportunities here for x to have multiple different matching outputs, right? Okay, now what about C? That's an equation, okay, but is that a function? Yes, Evan. So what's your explanation for that? Uh-huh. Yeah. So so Evan says this is just the equation for a straight line, right? Okay, because, and we can see that quickly because, as I mentioned, right, both of the variables here are just raised to the first power. So if you have equations where x and y are raised to the first power, that's almost certainly going to be a linear function. Okay, and Evan says further, well, if you take this and put it in slope-intercept form, that is, you solve it for y, then you'll definitely see that it's the graph of a line, right? So if we solve this equation for y, we would have 3y is minus 2x plus 6, divide both sides by 3, so you get y is equal to minus 2/3 x plus 2, right? So so we can definitely see that's the equation for a straight line, right? The slope is minus 2/3 and the y-intercept is 2. So if you graph this, if you graph this equation, you're going to get a straight line. And straight lines don't have loops in them, right? Okay, so you're not going to have any opportunity for having the same x with different matching y's, right? Okay, let's see. So the y-intercept we know here is 2. So this line crosses the y-axis at 2, and it has negative slope. So I just to make a very rough sketch of it, I would say it, you know, it's going to look something like this, because I know it's going to be decreasing from left to right because the slope is negative. Remember, slope tells me as x increases, right, y is in this case decreasing. So as x gets larger, the y values are getting smaller, they're going down. Okay, actually we sort of know what this point is also. That's the x-intercept. What is that? Can y'all see that from the equation, what the x-intercept is going to be? What'd you say, Robbie? 2. How do you find x-intercepts in general? 0 the y, right? So you substitute 0 for y and then solve for x. So if you plug 0 in for y here, you'd have 2x is 6, which means x is what? 3, right? Okay, so your middle arithmetic was a little off there. It's 3, right? Okay, so it crosses the x-axis at 3. Okay, so it looks like this, and you can see clearly, right, that none of your x values are going to have different matching y values, right? Okay, each x value you pick on the each value you pick on the x-axis will match up with one and only one y value. So that one is a function. So I didn't write them down. This one was right, okay, and this one was not, and this one is because it's a straight line. So all straight lines actually are functions, except one type of straight line is the exception, and we don't. I want to say we don't deal with that type of straight line often. That's not quite true, but one type of straight line is not a function. That is a vertical line. Okay, so vertical lines are not functions because notice that where that vertical line crosses the x-axis, that x coordinate is going to have lots and lots, millions and millions, right? Infinitely many matching y coordinates, right? Okay, well, in particular, it's going to have more than one matching y value, right? So so vertical lines are not functions, but any other sort of line, including horizontal lines, will be a function. Okay, all right. So, oh yeah, I did pretty good on that. Y'all remember that really very well. So that's good. All right, well, let's finish talking then about, since we know that, since we understand that definition for a function pretty well, let's go ahead and finish talking about functions. And I want to mention just a couple of special things about functions that you want to remember. Sometimes, functions are relations. So functions have domains. So that's the set of numbers that you can use as x coordinates, right? Okay, and functions also have range, right? That's the set of output values that you get for the function. But sometimes you'll be given a function expressed as a formula, and you'll be asked maybe what is the domain of this function, or for some reason you'll need to know what the domain of the function is. Okay, and so I want to just give you a little recipe for how you can determine what the domain of a function is if it's expressed as a formula. If it's expressed as a graph, you would look at the graph and determine the domain and the range from the graph, right? By looking at the graph. But if it's expressed as an equation, a formula, and you don't have the graph, then no, well, what do you do in that case? All right. All right. So it's really pretty easy for functions. You're going to assume by default that the domain is as large as possible. All right. So you'll assume by default that the domain is as large as possible. Now, sometimes that assumption is faulty because functions are often applied in practice, right? And in practice, your X values may represent some physical quantity that has a natural restriction on it. Like, for instance, the X in this formula could represent distance. Well, we usually don't measure distances as negative numbers, right? Right? So in that case, we would say, oh, well, the domain is positive numbers only because it doesn't make sense, or maybe I should say positive numbers and 0, not negative numbers, because it doesn't make sense if X represented distance to have negative distances, or if X represented, for instance, a weight, right? Okay, the weight of an object. Well, we don't usually have negative weights for objects, so again, it wouldn't make sense to use negative values for X. But if you don't have any restrictions like that from the context of how the function is being used, okay, so you don't have any physical restrictions on your domain, you'll just assume that the domain is as large as possible. So we would assume here that we can substitute as many values for X as possible into that formula. Well, what's as many values for X as possible? That would be all numbers, right? Okay, but that would be all real numbers. So our default assumption is going to be the domain is all real numbers. Now, that may not be true, so sometimes we have to work backwards and restrict the domain, okay? But our sort of our working assumption is, oh, the domain will start as all real numbers. Now, in this formula is very simple because this formula only involves very simple arithmetic, right? You're squaring a number. That means you're just multiplying it by itself. So that's just multiplication. Here we have multiplication. Here we have multiplication. And then you have some addition and subtraction. So you have very simple arithmetic operations in this formula. And you can carry those operations out with any number. You may need a calculator to help you. But theoretically, you can carry those operations out with any number. So there's nothing preventing us from using a domain here of all real numbers. So I would just say, well, easy. Domain here is all real numbers. So in the absence of some sort of physical restriction on your domain, right, or some sort of arithmetic restriction on your domain, just going to assume that the domain is as large as possible. So you can write all real numbers out in words. If you want to write that down in using interval notation as a set in interval notation, if you don't like writing out all real numbers, remember that we have an alternative way sometimes of writing out sets called interval notation. And interval notation would indicate a set of numbers between two given values. But for all real numbers, there's really no upper and lower boundary, right, on the set. So the way we indicate that is we use our infinity symbol. So if I put minus, remember that sideways 8 means infinity. So this means all numbers down to negative infinity. That's where our domain would start up to. And where would our domain end here? Yeah, positive infinity, right? So all numbers to positive infinity, which we write down this way. And then you just have to enclose these with some grouping symbols, and you will use parentheses in this case. Do not use square brackets because so you don't want to write the square brackets, because when you write the square brackets in interval notation, that means the boundary value is included in the set. But minus infinity is not really a number, okay, right? This is just no notation we use to indicate indefinitely to the left, right, on the number line. And so you cannot include this in your in your domain. And same thing for positive infinity. So it doesn't make sense to put a square bracket around the negative infinity and the positive infinity symbols. So that's how we would write all real numbers using interval notation, but I don't mind you writing it out in words, right? That's fine. Okay, so there's an easy example. They're not all quite that easy though. All right, so let's look at B and see what we do here. All right, now again, I'm going to assume that I don't know what the quantity X represents in the real world. So X could be, time, for instance, all right, or some other physical measurement. But I'm going to assume I don't know what that physical measurement is, right? So I'm sort of divorcing myself from reality here completely. All I'm thinking about is this formula and the arithmetic that's involved in the formula. All right. So again, we would start here with the assumption that the domain is as large as possible, right? Okay, which would be all real numbers. But now we have to be careful and restrict ourselves from numbers that are going to cause issues with arithmetic in the formula. Okay, because the arithmetic in this formula is a little bit more complicated than the arithmetic in the previous formula. Why is that? Because it doesn't look like a complicated formula. Well, the issue is this formula has division, and division is not as simple as multiplication and addition and subtraction. Okay, right? Okay, because in division, something bad can happen. What, Roddy? You cannot divide by zero. So you have to be careful here that you do not insert a value for X into this formula that will cause you to divide by zero. All right. And 1 is one of the bad values, right? Yeah. So Emil, you probably just saw that by inspection, right? If I plug 1 in for X, I'm going to get 1 minus 1 in the denominator, right? So I'd have 1 divided by 0, and there's where my problem occurs, right? So the number 1 is not in the domain, okay? That's not the only number not in this domain, though, all right? There is another one. So if you want to be methodical about finding those bad values, okay, we will just do the following. Take the denominator and set it to 0 and solve, okay? That will tell you the X values that will make the denominator here 0. So you just have an equation to solve, right? So let's see if we can solve this equation. This is a quadratic equation because the unknown is squared, okay? And we have many techniques for solving quadratic equations where the unknown is squared. But our favorite technique is to set the equation to 0, which this one is already set to 0, and then try to factor the left-hand side of the equation. Okay, try to factor. Can you factor x squared minus x? Is there an easy way to factor that? Well, it's kind of like dividing by x, but that's not quite how you want to say it. Factor out the x, right? Okay. So you can factor out an x from x squared minus x, and that would leave you x times x minus 1 in C's here. Okay. So factor out an x. Now, the reason that factoring technique is useful is a very fundamental principle of arithmetic now here applies. Okay, so this is a very important idea and very simple idea that you learned in grade school about real number arithmetic. When you multiply real numbers together and get 0, that only one way that can happen. One of the numbers has to be 0, or both, right? But one of them's got to be 0. You can't form a product and get 0 unless one of the factors is 0. Okay, so that means then we can automatically deduce that x is equal to 0 or x minus 1 is equal to 0. And if x minus 1 is equal to 0, that means x is equal to 1. So you see, Emil, there was your answer. 1 cannot be in our domain because it makes the denominator 0. But there's the other one. X cannot be 0. Okay, you probably could have seen that by inspection too, without going through this formal process. But this is a little bit safer. Okay, so there are the two numbers that we cannot put in the domain of this function, 0 and Anything else though is fair game. All right, so our domain here is, I'm just going to write it out. I think it's easier just to write it out. All real numbers except 0 and -1. If you want to write that in interval notation, you can do it, but it's a little bit complicated because when you take 0 and 1 out of the real number line, it cuts the number line into 3 pieces. You draw a little picture of that. Here's a number line, like the x-axis, right? And when you take out 0 and when you take out 1, so I'm going to take these two out, you get 3 pieces. You get the piece on the left, the piece in the middle, and the piece on the right. And you can write those 3 pieces down. Well, so what would we write? So what's this piece on the left in interval notation? Where does it start, Emil? What's way out here? -infinity. And it goes up to 0, right? But it doesn't include 0, so you have to put a parenthesis there. If you put the bracket, you're including the 0, but the whole point was to not include 0, right? Okay, and then what's the piece in the middle? That's from 0 to 1, right? Not including 0 and not including 1. And what's the piece on the far right? That's 1 out to infinity, not including 1. And then you can't include infinity because infinity is not really a real number. Now, you just combine those 3 pieces. And the way we combine sets in mathematics is taking the union of the sets. And you indicate that with this little stylized U. So it's actually a little, to me, it's a little bit more clumsy to write this set in interval notation than it is just to write it out in words. I'll take either way. Okay, either way is fine. Mathematicians are happy with however you want to write it down. Okay. Yeah, probably in the homework. Having said, I'll take it either way. WebAssign probably is going to want this. Right. Okay. So if WebAssign wants that, it will say use interval notation. This is interval notation. This, of course, is just English. All right. So that problem illustrates the first step in my recipe, which is if you want to find the domain of a function represented by a formula, okay, if it's got fractions in it, set the denominator of the fractions to 0 and solve. Those numbers have to be out of the domain. Okay. All right. Now let's look at the other case here. All right. So here we have a simple formula. G of x is square root of 9 minus x. And so again, you would assume to start with, since we don't know what the quantity x represents in the real world, right? We don't know what x is measuring. We would just assume the domain is as large as possible. That would be all real numbers. And then we look at the arithmetic in the formula and see, okay, is the arithmetic in the formula going to cause us any difficulty? If it doesn't, then we're done. The domain is all real numbers. But here, the arithmetic in this formula involves square root, and square root also is a problematic arithmetic operation, okay, like division. What's the problem with square roots? Or it could be 4th root or 6th root. What's the problem with even roots in general? But most often it's square root. You cannot take the square root of a negative number. Right? You cannot take the square root of a negative number. That's an issue, correct? So so we have to avoid putting an x that will give us a negative number under that radical. So for instance, if we try to compute g of 10, we're going to run into trouble because we will get, yeah, the square root of -1. And if we're just restricting ourselves to real numbers, there is no real number that's a square root of -1. So so what that tells us is I don't want 10 in my domain. Okay, so my domain is not all real numbers. It doesn't include, for instance, 10. So how do we figure out what the domain is? Well, here's the second part of my recipe. Okay, so there it is right there. It just says set the radicand That's the expression under the radical. Set that greater than or equal to 0 and solve that inequality. Okay, that will tell you the numbers you can keep in the domain, not the ones you have to exclude, but the numbers you can keep in the domain. So let's do this. So we take 9 minus x, we set it greater than or equal to 0, and we want to solve that. Okay. Well, that's solving an inequality, which is very similar to solving an equation in many instances. But there is one thing you have to be careful of. So you could solve this one pretty easily by just moving the minus x to the right, and you would get 9 greater than or equal to x. Or if you read that backwards, that says x has to be less than or equal to 9. So numbers in your domain only can be numbers less than or equal to 9. So what are numbers less than or equal to 9? Where does that set start at? Yeah, it starts at minus infinity, right? And where does it go up to? 9, right? Okay, because you want numbers less than or equal to 9. And since it's equal, you can include 9. So you can, there finally a mill, we can use a square bracket. Okay, so there's what our domain looks like there. It's only numbers from minus infinity to 9, but stops at 9. So cannot include 10 or 9.1 even, right? Okay, not in the domain. I want to show you one other thing about solving this inequality, though. It's easy to forget. Solving inequalities is often very similar to solving equations, except there are exceptions. Inequalities are not equations. We could have also solved this inequality by bringing the instead of the minus x to the right, we could have brought the 9 to the right. And we would have had minus x bigger than or equal to minus 9, because the 9 sign would change when we got to the right-hand side of the inequality. Well, you got to get rid of the minus signs, right? So you can do that easily by dividing both sides by -1, or you could also think of it as multiplying both sides by -1. But when you multiply or divide both sides of an inequality by a negative number, you have to reverse the direction of the inequality. You have to reverse the direction of the inequality. So we would get positive x and then switch the inequality less than or equal to positive 9. That's the same answer, right? It's just written backwards. So there's one thing you have to remember about solving inequalities. When you multiply or divide an inequality by a negative number, you have to reverse the direction of the inequality. You can say that I'm doing the same thing with equations, but of course, when you reverse an equation, you still get an equal mark, right? But when you reverse an inequality, it's different. Why is this true, by the way? You can just take simple examples. -2 is less than or equal to -1, right? -2 is to the left of -1 on the number line, correct? But when you divide by -1, what happens? You get 2 here, and here you get 1. So to keep this true, what do you have to do? Obviously, you have to reverse the direction of the inequality, right? So that's why you have to be careful about inequalities and multiplying and dividing by negative numbers.
So we multiply
What now? Okay. All right. So there it is. There are the two sort of kind of rules you have to remember when you're dealing with functions represented by formulas, which we're going to be dealing with all the time. Okay. So keep these two rules in mind. All right. Okay. In finding the domain of such functions. What about range? So these are the sets that we can substitute for x. I wonder what sets we're going to get as what set we will get as output from these formulas. That's a much more difficult question. Okay. Yeah. I'm going to pass it out. Right. So finding the range of a function represented by a formula is hard. Okay. You can find the domain pretty easily just by following these rules sometimes, but finding the range is tough. Okay. And that's really a question that is addressed in calculus, right? That's really a calculus question. How do I find the range of a function represented by a formula? Of course, if you turn the formula into a graph, you might be able to do you might be able to figure the range by looking at the graph, right? Okay, but without turning it into a graph, finding the range is tough. Okay, but calculus really addresses that question. So that's really a calculus question. But domain is just an algebra question. All right, I'm going to give one to you while I'm passing out the roll sheet. So you guys online, right? Okay. So I have both things combined in this one problem, both situations that you have to watch for combined in this one problem. So I want to know what's the domain of this pretty typical function, h here, x over the square root of x plus 1. What numbers can we substitute for x? What's the domain? And now I'm going to, while people are doing that in class, I'm going to pass out the roll sheet. Remember that. See if I can get everything. I don't think I can get everything on one page. No. So the two rules are set denominator to 0 and solve. That's one rule. And then set radicands greater than or equal to 0, things under radicals greater than or equal to 0, and solve that inequality. So you have both denominator and radical in this problem. Sorry, I'm missing. There was a long chats there, guys online. I'm sorry, I was not seeing all those good things. So everyone in class. Okay, so let's talk about this one. We don't have to spend a huge amount of time on this. So here in this formula, which is a pretty simple formula, but it is complicated by the fact that it has a square root in it, right? Okay, so that complicates the domain. By the way, if that were a cube root, if this were a cube root, which you would denote by putting an index of 3 there above the radical, or a fifth root, we don't often deal with fifth roots, but it's possible, or a seventh root, that's even more rare. If you have an odd root, none of this applies, okay? All right, because you can take an odd root of any number, positive or negative, all right? It's only even roots that are issues, all right? And of course, the root we deal with most frequently is square root, sometimes cube root, few times fourth root, right? Okay, so but square root by far is the radical you'll see most frequently. So so that's why we an odd root 3, 5, 7, right? Okay, yeah, any odd number, right? But you can take an odd number of anything, so doesn't create problems. But it's even number roots like square root or fourth root, especially, or sixth root, which you will rarely see. Those are the roots that cannot take an even root of a negative number. So you cannot take a square root of a negative number. So that's going to cause us an issue here in this formula, and we cannot divide by 0, right? So since we have division in the formula, we have to be careful about not dividing by 0. So where do y'all want to start in trying to narrow down that domain from all real numbers? What now? Start deal with the square root first. Okay, so so to deal with the square root, we said what? We take the quantity under the expression under the square root, right? That's called the radicand technically, and do what with that? Make it greater than or equal to 0, and then solve that inequality. It couldn't be any easier to solve, right? Just shift the -1 to the right hand side. I'm sorry, the 1 to the right hand side, and it becomes negative. So we know that automatically x has to be bigger than or equal to -1. So we're already dealing with a domain that cannot include anything less than a -1, right? So let's write that down to start with. So let's see, that set begins at what? -1, right? And goes out forever, indefinitely to the right. So so our domain kind of looks like this, but we may have to restrict this a little bit more because we also do not want to do what? Divide by 0, right? You do not want to divide by 0. So to avoid dividing by 0, take the whole denominator, including the square root part, and set that to 0 and solve that equation. Okay, so now we have to see if we can solve this equation. To solve this equation, I would like to get rid of the square root, but the square roots, you know, are not friendly, right? So how can I get rid of the square root? Square, right? Yeah, just square that, but then make sure you square the other side as well, right? So then we have x plus 1 is, of course, it's so easy to square 0. So now we have x plus 1 equals 0. And now that's so easy to solve, right? That means x equal -1. So what does that tell us? You can't have -1 either, right? And this set does include -1, right? Barely, but it does. So we have to cut that out. So how do we cut that out? With a parentheses, right? So the bracket there just becomes a parenthesis, right? So that was easy. So I had to make that one slight adjustment there, and there's the correct domain. So numbers from -1 to infinity, but not including -1, right? That's it. Okay. All right. Now one other, again, so these are just kind of function topics that you need to be aware of. In practice, especially in practice, you will often run into functions whose formulas are a little bit more complicated than just a single expression. Such functions are called piecewise functions, and we need, because their formulas consist of multiple pieces, and we need piecewise functions sometimes to model more complicated phenomena, okay? So in the real world, you know, the things that you're modeling, the quantities that you're trying to model and predict, they sometimes can, you know, fluctuate a lot. They can be complicated. And so sometimes we need complicated functions to model those complicated real world phenomena. And one way we do that is through what are called piecewise functions. So piecewise functions, again, are functions where the formula for the function consists of several pieces. Here's a piecewise function where the formula has two pieces. Okay, but you can have more than two pieces, so you can have multiple pieces in your formula. And if you graph a piecewise function, we're going to graph this one, then the graph will also consist of multiple pieces. All right. Okay. Let me explain the way piecewise functions work, though. All right. Although it's pretty easy to see from the way the formula is expressed here. Okay. So this function f, right, has two different formulas. Of course, you cannot apply both formulas simultaneously because you wouldn't have a function, right? Okay. See what I'm saying? If you are trying to calculate, for instance, f of 3, and you used both formulas here, that wouldn't work, right? If you use the first formula, what's f of 3? That would be 2 times 3 plus 1 is 7, right? But if you use the second formula, you get 3 minus 3 is 0. Well, you can't use both formulas because then that input would have how many outputs? 2, right? Okay, and you no longer have a function. All right, so the idea is you're only going to use one of the formulas for each input. Obviously, use one of the formulas, and that depends on where your input is in the domain. Okay, so different pieces of the domain will use different formulas. So if we were trying to calculate f of 3, again, using that as an example, well, let's see, where does that fall in our domain? Is 3 less than 2? So is it on the left-hand side of the domain? Or is 3 greater than or equal to 2? Is it on the right-hand side of the domain? Obviously, it's greater than or equal to 2, right? Okay, so that means we use this formula. So what's the correct output here? Yeah, 0. So, that tells us something. 3 is a X-intercept of this function, actually. Okay, because the y coordinate turns out for 3, the y coordinate turns out to be 0. Okay, so that's the way piecewise functions work. So if you're trying to compute the y-intercept of this piecewise function, that would be compute f of 0, use x input of 0. Well, let's see, where does 0 fall in the domain? 0 is less than 2, correct? So that means we use this formula. So we get 2 times 0 plus 1, and that is 1, right? So the y-intercept we know now. And so forth. So you can calculate f of really any input. The domain for this function is actually all real numbers. Because think about it. Any real number is going to be either less than 2, correct? Or it's going to be greater than or equal to 2. So your domain here is any x, okay? Domain is all real numbers. Well, it's pretty easy to evaluate piecewise functions if you just keep in mind how the piecewise formula works. How is the graph going to look? So let's see if we can make a graph of this piecewise function. So as I mentioned, since the formula consists of two pieces, the graph also is going to have two pieces to it. We're going to have a piece that corresponds to 2x plus 1, and we're going to have a piece that corresponds to 3 minus x. Think about those two formulas separately. 2x plus 1, if you graph that formula 2x plus 1, what sort of graph will you get? What sort of picture do you get? It's going to be a line, right? Okay, yeah. So this piece looks like a line. What about 3 minus x? What sort of graph would that give you? You graph that, what? That's also a line. Yeah, that's just a straight line too. So so when you graph this all together, when you graph this piecewise function, you're going to get two straight lines. That's it. But it won't be the same line, okay? The lines are going to be different from one another. All right, so let me just for convenience here, let me number these two pieces. So we'll call this piece 1 and this piece 2. So let's make the graph of piece 1. It's pretty easy to graph that, but let me do it rather carefully by let's let's plot some points, okay? So we know the graph is going to be a straight line, but let's plot a few points here. So that means I'm going to pick some X values, plug them into the formula, and see what the matching Y value is. Make sure you pick something less than 2, though, right? Okay. So can y'all suggest something for me for X? 0? That's fine. Okay, 0 is less than 2. And what's the matching output there? 1, right? Because 2 times 0 plus 1 is 1. Okay. All right. What's it? Can y'all pick something else here? What? Emil, 2? Emil, though, we're plotting piece 1. So I cannot use 2. Oh, -2. There you go. All right. So if I plug -2 in for X, what do I get? 2 times -2 plus 1 is what? I think that's -3, isn't it? -4 plus 1 is. There you go. All right. Actually, that's enough because we know the graph here is what? Already? Y'all told me a moment ago. What, when you graph 2x plus 1, do you get? A line. And we already have 2 points on the line. Well, that's all you need to graph a line, right? Is 2 points. But let's be a little bit careful. Let's pick another value here just for fun. So what do y'all want? I suggest 1. 1 is less than 2, right? What's the output? 3? 2 times 1 plus 1? All right, so let's do those then. So let's see, 0 and 1 right there. 1 and 3, I think, is right there. And then what was the other one? -2 and -3 down here. Are those on a line? Yep. So just connect those points with a straight line. Now, you know, of course, the line is a line, so it goes indefinitely from left to right. But I cannot extend the line indefinitely to the right because where do I have to stop at? 2. So let's keep going until we think we're something like there, right? Okay. So stop at 2. Be sure, don't go past 2 because that'd be a mistake. All right, now let's do this one quickly. This one also should be easy, right? So what's some X values you want to pick? You got to pick something bigger than 2 for me, though. Well, 2, right? So that would be 1. What else there? 3 is 0. Yeah, we knew that a moment ago. And then maybe one more. 4 is -1. Okay, so let's quickly graph those. 2 and 1, 3 and 0, and 4 and -1. Pretty boring line there, right? The slope is -1, so you get a line that looks like this. Make sure you started at 2. Now here's so there's really what the graph looks like. This piece is continuing to the, this piece is continuing on the right, and this piece is continuing on the left. Now, what often happens here, though, when you're graphing piecewise functions is where these boundary values occur, right? Where the domain switches from one formula to another, those are often confusing on the graph, okay? If you didn't have the formula and you were looking at this graph, just the graph, and someone asked you, what's f of 2? But you didn't know the formula, right? You just had the graph. If someone asks you, what is f of 2? You might be a little bit confused, right? Because you might think, okay, f of 2, it might be this number or it might be this number, right? How am I supposed to know which it is if I'm just looking at the graph? It can't be both, because if it were both, you wouldn't have a function, right? Okay, so it's got to be one or the other. It's either this point, this x coordinate, which is 1, or it's this x, this y coordinate, which I don't quite know what that is, right? What? Go ahead. What are you saying now?
Oh, like, and trying to find number 2, most likely tell which one that you got number 1 or number 2.
Yeah, but what if you don't have the formula, though? What if you're just dealing with the graph, Emil, and the formula wasn't given to you? Well, the answer is you want to make the graph clear. Okay, so when we're drawing the graph, yeah, we have to make it clear which is the right answer. So we use open and closed dots to do. Okay, that's just to make it friendly to the reader, so they will understand what f of 2 really is. So what is f of 2 really? We know it's down here, right? So here we would put a nice big closed dot to make it clear that that dot is part of the graph. And then up here, we will put an open dot to make clear that that is the end of that piece of the graph, but that point is not really part of the graph. Okay, and then someone can look at that and say, oh yeah, I see f of 2 is really down here at 1. It's not really up there, okay, at 5 or whatever that was supposed to be. All right, okay. So so where you have the breaks here in the graph, when you're graphing a piecewise function, you have to be careful to use open and closed dots just to make sure that the reader understand what's really happening on the graph, and vice versa. If you're reading the graph of a piecewise function, you look at the open and closed dots to help you understand, right? What the correct outcome. Yeah, that's why it's not ambiguous, okay? Because we cannot have a closed dot in both places, because then we don't have a function. Okay, all right. So I'm just going to get this just one example only on piecewise functions. I don't want to dwell on this. Okay, we're not going to be working a lot with piecewise functions, but they do come up from time to time. But especially in practice, you'll see them frequently. Okay, because again, they're useful for real world phenomena, which can be quite complicated and have various behaviors for various parts of the domain. Okay. All right. We're going to stop there for a few minutes. So we're going to take our break just a little bit early, and then we're going to come back and talk about angles. Right. So we're at a convenient stopping point. You guys online, do y'all have questions there that you want to ask me? Okay, so we'll recommence at 15 after. So let me pause the tape here. Okay, so we're starting again, but when I say starting again, we're really moving on to something that's quite a bit different, at least initially, than what we've been thinking about before. So we've been talking about triangles, of course, since right at the first day of the class, right? We've been talking about triangles, but we're gonna now zoom in on a really ancient topic. All right, so ancient that it predates recorded history, so it comes from antiquity, and we know it comes from antiquity because it shows up in the very earliest writings that we have from different cultures, and that's the study of right triangles. And so at first this is going to feel quite different from algebra, but then we're going to the sort of algebraic sorts of things that we've been doing for the past few classes, but we're going to take this topic of right triangles once we learn about it in sufficient depth, and then we're going to tie that back into our what we just discussed, and that's functions. Okay, because we're going to use right triangle geometry to develop a new category of functions that will be unfamiliar to you, different from the types of functions that you've seen in previous classes, or that we've been working with as examples in this class. Okay, and these are called the trigonometric functions. But prior to that, we're going to talk about just the study of right triangles. So those are triangles that have 90-degree angles in them, embedded in them, right? And that subject is called trigonometry. Okay, so that's what we're embarking on right now, is trigonometry, learning about trigonometry. And but we have to start at kind of a very elementary spot, because triangles have angles in them. So and right triangles have 3 angles as well, except one of them is a 90-degree angle, but it has right triangles have 2 other angles in them, right, that are not 90-degree angles. And so we need to talk a little bit more closely first about angles, the terminology that surrounds angles, and in particular how we measure the size of angles. Okay, which is really conceptually quite easy, but but it's a little bit different in calculus than in your naive understanding of how we measure angles. So that's what we're going to discuss here today. Okay. All right. But let's start first with just what is an angle. Okay. So intuitively, you know what an angle is. I'm just going to give you kind of the formal mathematical definition, but your intuitive understanding of angle is correct, right? Right. You understand what an angle is, right? But if we want to give a precise mathematical definition, we would say an angle is formed by taking two half lines. Okay. So half of a line. So half a line extends infinitely in one direction, right? Okay, so I've drawn two half lines here. One of them I've drawn horizontally. Doesn't have to be drawn horizontally, but just to make the picture easy, I drew one of the half lines horizontally. So I called that one R1, and then I drew another half line here, R2. Now, notice that I connected these two half lines at their endpoint. Okay, so I gave them a common endpoint, and when you do that, when you take two half lines and you draw them from the same endpoint, half lines are going to have an endpoint on one side, right? Okay, because you only have half of a line. So if you take two half lines and draw them from the same endpoint, you get an angle. Okay, a picture that you get is called an angle, right? So you see in this picture an angle. Actually, you get two angles, right? If you want to think of it, you really have two angles, right? Here I have the angle inside the two half lines, and then I have this angle outside of the two half lines as well. One of these is an acute angle because it's less than 90 degrees, right? This one. And then you have a larger angle here, an obtuse angle. This angle on the outside is an obtuse angle because it's bigger than 90 degrees, okay? All right, so anyway, that's what an angle is. It's two half lines that are joined at a common endpoint, okay? Now, angles we frequently give Greek letter names to, okay? Or more precisely, we often give Greek letter names to the size of angles, okay? And so let's discuss here how we measure the size of an angle. All right, so to measure the size of an angle, we pick one side of the angle, right? Remember, because the angle has two sides to it, right? The two half lines. So you pick one side of that angle, it doesn't matter which one, and you're going to call that the initial side of the angle, all right? And then the second half line, you'll call that the terminal side of the angle. And it's just kind of arbitrary which one you pick as the initial side and which one you pick as the terminal side, okay? And then the measure of the angle is the amount of rotation that's required to take to lift the initial side to the terminal side, okay? So think of it as kind of a physical process here. So in this first picture, let's call R1, since I labeled it as 1, let's call R sub 1 the initial side of that angle. And then we'll call R2 the terminal side of that angle. All right, but you could switch the initial and terminal side again. That's just purely arbitrary. All right. And now think of taking R1. I'm trying for y'all to see here what I'm doing. What I'm showing the class here. Think of lifting that initial side and rotating it. You want to keep the endpoint in the same place though, right? So think of rotating around that endpoint until you bring R1 to R2, all right? That amount of rotation that would be required, that is the size of that's the size of the angle. That's how we measure the size of the angle. So it's amount of, you can think of it as amount of rotation, right? This is the classical ancient way of measuring size of angles, okay? And developed by the Babylonians, okay? Again, a long time ago, all right? Now, in developing this method for measuring the size of the angles, the Babylonians decided, okay, but it wasn't arbitrary. It wasn't arbitrary, okay? They didn't pull this number out of thin air. But the Babylonians decided that one full rotation, if it took one full rotation to bring the initial side to the terminal side, Okay, they said that would be 360 degrees. So the unit of measure they used to measure angles was degrees. Okay, and in one full rotation, so if you had to go all the way around to take the terminal side, I'm sorry, the initial side to the terminal side, that they said that's 360 degrees. That's one full rotation. And then any part of a rotation, they just took that as a fraction of the 360 degrees, right? Okay, so if you look here, right, okay, if you want to swing R1 up to R2, right, that looks like that would take maybe an eighth of a full rotation, right? Okay, right, maybe an eighth of a full rotation. So that would be an eighth of 360 degrees, which would be what? Well, 360 divided by 8. I think that's 45, right? Yeah. So the Babylonians might have said, oh, the size here of this angle, this first angle that I've got drawn, where I'm bringing R1 up in counterclockwise, right, to R2, the Babylonians might have said, oh, that's 45 degrees, because it was an eighth of 360 degrees, which is one full rotation. Now, if you make the rotation counterclockwise, the size of the angle is considered to be positive. So counterclockwise is positive, all right? Babylonians did not have clocks, so they were not thinking of trying to make a clockwise positive, right? Okay, so it would conform to a clock, all right? Babylonians didn't have clocks. So I guess arbitrarily, Babylonians just decided if you were sweeping in this direction, right, okay, from what I would say is right to left, then that was positive a measure, okay? If you did the rotation in the other direction, that would be negative, okay? Actually, I don't know how Babylonians thought of negative rotation, because they didn't deal with negative numbers either, so we would have to consult with an expert here to say, how did Babylonians think of negative rotation? All right. So look, in this picture, again, you've got two angles, right? Okay. So this angle, I'm going to call that the size of that angle theta, or I'll just, you know, also just say I'm going to call this angle theta. This is the Greek letter theta. Okay. So it's a 0 with a line through it. That's the Greek letter theta. Okay. Yeah. And so I would say that theta is positive measure, okay, because we moved R1 in a counterclockwise direction. In the for the other angle, though, okay, this is the Greek letter alpha. So for alpha, I would say that is negative measure, because I thought of sweeping R1 in the clockwise direction. Okay, so if you form angles clockwise, you're going to have negative measure. If you form angles counterclockwise, you're going to have positive. All right. What was? A D?
He is a boy or what?
Okay. Well, it's none of those things. It's not an English letter. Yeah, or I can't say English. What's the Phoenician alphabet? It's not in Western alphabet symbol. Okay. Or modern Western alphabet. Yeah, so that's the Greek letter alpha. Here's another picture of angles, right? Okay, so here we've I've got, let me move the chat box out of the way here. So I think that horizontal line, again, I'm calling that R1. Here is my R2, right? So they're emanating from a common endpoint. So you get an angle, and actually get two angles here. And depending on how you want to move that initial side, right, to the terminal side, you get either an angle with positive measure or an angle with negative measure. So if you sweep R1 in a counterclockwise direction to move it to R2, the size of that angle, which I'm calling beta, this is the Greek letter beta, it would be positive. But if you think of moving R1 in this direction to move to R2, you would get an angle with negative measure. This is the Greek letter mu. Okay, so so mu here is negative what? Mu, mu, yeah. Okay, so you may be familiar with these from variant names, right? COVID variant names. So there's beta and alpha. I don't think they have a. Do they have a? No, there is a mu. That's one of
Yes,
the. That's one of the less famous variants, but there is a mu. Okay. All right, so not a theta yet though. So and we use theta a lot, so hopefully we won't get to theta before the class is over with on the COVID side. All right. All right. So this is just repeating what I just said. All right. So all of this is just a repetition. Let's see if we can estimate there. Let's see if we can guesstimate here the size of some of these angles in this picture. All right. So if the angles are drawn just right, you can sort of get a good, you can get a good visual estimate for the size of the angles in degrees. All right. So let's look at theta here. Okay. So I formed theta by moving R1 up to R2 in a clockwise direction. I'm sorry, counterclockwise direction. And I did also beta. I moved R1 up to R2 in a counterclockwise direction. So both of these angles must be positive, right? The question is how far, how many rotations, right? Or what fraction of a full rotation did we have to move R1 to get to R2? Beta is pretty easy. How much of a revolution do you use to form the angle beta? Well, it's what now? Yeah, that's what I'm talking about, right? If you're moving R1 to R2, that would be 1/4 of one full revolution, right? See, one full revolution would be, of course, all of this, right? So if we're just moving R1 up here, then you just have 1/4 of a full revolution, right? So that's 1/4 of 360 degrees, which is what? 90, right? Okay. So we can see there that beta apparently is about 90 degrees. And you put the little circle there to indicate the unit of measure, right? Okay. What about theta then? I think we already discussed this, right? It's 45, right? Because we moved theta just half as far as we moved R1 half as far to form theta, right? As we did to form beta, correct? So theta is half of 90, or 45 degrees, right? So these are very familiar angles to us. We'll often be working with 90-degree angles. Those are right angles, right? Okay. And we'll often be working with 45-degree angles like this one. Okay. So we use those angles a lot. Here's another angle that we use a lot. So imagine you take R1, and so this is R2, this picture, it's the back half of the x-axis. So imagine you just sweep R1 over here, right? And you just get this fully open angle, okay? How big is that angle then? So that's mu, what? 180, right? That's half of a revolution, right? So mu there is, looks like it's 180 degrees. Now, alpha here is harder to estimate. So here we're really going to have to think about it, okay? Right? First, we formed alpha by rotating R1 in a clockwise direction. So we know immediately that alpha is negative, right? It's less than 0, okay? Because we formed alpha in a counterclockwise direction. So, Ravi, you said what? Minus 135. So Ravi's thinking this alpha is approximately minus 135 degrees. So why do you think that, Ravi? You're going clockwise, so it's negative, right? And yeah, first you go past 90, right? Okay, because you have to sweep past this 90-degree angle. So you've already got down to here, right? Which is minus 90 degrees, correct? And then you have this other little piece, right? Okay, and you're saying, oh, I think this other little piece is maybe 45 degrees. Yeah, I don't think so. I think 45, I think, would be more like this. Yeah, so maybe 60, right? Maybe we went another 60 degrees, right? Okay, we're only estimating, so we're not going to get it exact, right? Okay, but I'm thinking 45 is more like this line, right? Okay, and so we went a little bit past 45 degrees, maybe 60 degrees. So maybe a better would be, you say minus 150? Yeah, which is 90, and then another maybe negative 60 degrees right here. Yeah, so I think that's good, minus 150. But again, we're just visualizing it, right? So of course we're not going to exact. Right, so all of that is just conforms to your, again, just your naive understanding of angles, right? Okay, except maybe the negative angles not used to. But when we're studying right triangles, we don't measure angles as negative anyway. So we'll kind of put the negative angles aside temporarily while we're dealing just with right triangles. But we're going to come back to them. Now, in calculus, though, there's another method for measuring angles, and this is much less intuitive. All right, so this you're going to have to practice a little bit with to get comfortable. Right, it's not going to be immediate. Not going to be immediate. All right, so trust me on that. Okay, but the more you deal with measures angled in this, angles measured in this different unit of measure, you'll get better at understanding it. But we're not going to completely switch away from degrees because degrees are very convenient. So we'll be moving back and forth all the time. Okay, between this sort of calculus way of measuring angles and then your more classical way of measuring the size of angles. By the way, I mentioned the number 360 was not random. Okay, right, for incorporating 360 degrees in a full revolution. Although this is not known because this happened in antiquity. All right, so before recorded history, it's not known why the number 360 was chosen as for the size of one full revolution. It's probably because 360 has lots of divisors. There are lots of numbers that divide into 360. Okay, yeah. So and so that makes it convenient for doing arithmetic. Okay, especially you don't have a calculator, right? Okay, and of course the Babylonians didn't have calculators, so so it's felt that that's how they came about using 360, because it's just easy for doing arithmetic with 360 because you can divide it in lots of different ways, right? Okay. Here's now our new method, though, for measuring angles. Okay. All right. So you have to think about this. All right. Again, it's not as intuitive as the Babylonian method. All right. So we're going to take the angle, all right, that we're trying to develop a measure for, right? Okay. And we're going to put that onto a rectangular coordinate system. So the Babylonians didn't have rectangular coordinate systems, right? So they could not have done this, okay? But we're going to put it onto a rectangular coordinate system. And of course, we're going to put the vertex of the angle. By the way, that I'm not sure if I emphasize that, but that point where the two half lines come together, that's called the vertex of the angle, right? So we're going to put the vertex of the angle right at the origin. And then the initial side of the angle, we're going to lay it along the positive side of the x-axis. This is called putting the angle in standard position. Okay, so if you draw the angle, so the vertex of the angle is at the origin, and the initial side of the angle, what you're counting as the initial side of the angle is along the x-axis. That's called standard position. Okay. All right. Now, also on this Cartesian coordinate system that you have drawn here, right, we're going to draw a circle with radius 1. Right, so we know that, by the way, we know the formula for this circle, right? It's going to be x squared plus y squared equals 1 squared, or x squared plus y squared equal 1. So you're going to put a circle with radius 1 right there on that rectangular coordinate system. Of course, that angle is going to cut through that circle, right? Okay, that angle is going to cut through that circle in two places. Okay, because the circle completely surrounds the vertex, right? So the two half lines have to cut through that circle in two places. Now, that the length of that arc between the two sides of the angle, the length of the arc on the circle, okay, that is going to be this, that's what we're going to call the size of the, right? By the way, this arc, we say, left off some words here. We would say this arc on that circle subtends, that's the technical word, subtends the angle. And the length of that arc, right, between those two sides of the angle, that is going to be the measure of size of the. Okay, that's already a little bit goofy, right? So in this method of measuring the size of angles, notice that the size of the angle is a distance. Okay, size of the angle is actually a distance because it's the length of this. It's the length of this arc. Right? Okay. This method, by the way, is called Radian Measure. So on your calculator, on your scientific calculator, you know you can switch between degree mode and radian mode. So you can switch between measuring angles in degrees or measuring angles in radians on your calculator. The shorthand for radian is usually RAD. But if we write down the size of an angle and we leave off the unit of measure, then by default, it's going to be radians. It's not going to be degrees. Okay. So if you leave off the unit of measure, it's understood that the angle is measured in radians. All right. Let's try measuring some angles in radians. Okay. Because this is going to take some practice. And you got to start with some easy examples. All right. So what I've done here is I've drawn some angles, okay, and we're going to just write down their radian measure. All right. So here's the first angle that I've drawn. I've drawn an angle that's one full revolution. So I'm calling that theta. I'm going to call all these angles theta. All right, and my angle theta is one full revolution. Right. So remember now, in radian measure, you're assuming that the initial side of the angle is along the x-axis, right? The positive side of the x-axis. And so then I've drawn, starting from the positive side of the x-axis, I've drawn around one full revolution. So of course, the terminal side of this angle will also be on the x-axis, because this is a completely open angle. It's one full revolution. So there's our picture of theta. By the way, we're measuring theta. Is it going to be positive or is it going to be negative?
Positive.
Yeah, it's positive because I've drawn theta clockwise, right? I mean, counterclockwise. Now, again, what is in radian measure, what's the size of theta? Here's my unit circle. So guess what? The size of theta is going to be the distance all the way around the circle. Because remember, we form theta as one full revolution. So it's the distance all the way around that circle. What's the distance around a circle called? The circumference. So if I can calculate the circumference of this circle, I will know the radian measure of this angle theta, one full revolution. What is the circumference of this circle, though? Remember the formula for circumference? It's 2 pi r. Yeah, y'all are right. Okay. So it's 2 times pi times the radius. But remember, I very conveniently chose the radius of the circle to be what? 1. So I get 2 pi times 1. And so it's just 2 pi. And this is radians, which I can abbreviate as RAD. So there's the size of theta in radians. It's kind of an awkward number. It's 2 pi. That's not as convenient as 360, right? Okay, but there it is. Okay, that full revolution, it's 2 pi radians. Now, look what I can do though. I also know according to the Babylonians, that one full revolution in degrees is how much? That's 360 degrees. So look what you can do here. You can divide both, see this equation? Divide both sides by 360. And look what you get. You get 1 degree is 2 pi over, I should have written the 360 over here. It's 2 pi over 360, which reduces to pi over 180. So 1 degree is, it's kind of a weird number, but there it is. 1 degree is pi over 180 radians. That's 1 degree. So if you had an angle measured in degrees, and frequently we're going to have angles measured in degrees because it's very convenient to measure angles in degrees. How would you convert that to radians? Looking at this formula. Times whatever you have by pi over. So if you have 45 degrees, multiply that 45 by pi over 100. If you have 180 degrees, multiply that by pi over. Okay. So you can convert from degrees to radians easily, although you'll get awkward numbers by multiplying by pi over. Right? Now we could have played this game backwards, because we had 2 pi radians, again, was 360 degrees. Now divide both sides by 2 pi. So look what happens. Over here, you get what? 1 radian is over here, we get what? 180 over pi degrees. So if you want to convert radians to degrees, and that's something we often want to do, convert radians to degrees, we often want to do that because it's very hard to understand sometimes how big an angle is when someone tells you, oh, I have an angle and it's 10 radians, and you're like, yeah, what does that mean? You know, how big is that angle? You know, but if you convert it to degrees, you can think about it really easily. Okay, well, the way you do that is, according to this formula, take the number of radians and multiply it by 180 over pi. Okay, and that will 2. Again, sometimes that gives you awkward numbers because this formula involves pi, but that's just that's life. Okay, right? That's what we have to live with. Let's try another one. What about 1/2 positive revolution? Can y'all see this angle? So it started here. That's the initial side, and then the terminal side is here. I just opened that initial side in a counterclockwise direction to the back half of the x-axis here. So that's half of a revolution, right? So how big is that going to be in radians? That's the length of this arc from here to here. Well, not quite a mil, right? Okay, because what's the whole circle, a mil, and what's the circumference of the whole circle? What did we say? But the r is what? 1. Yeah, this circle has radius 1. So the whole circle is 2 pi, right? Okay, so what's half of the circle? Pi. So theta here is pi radians. Half of the circumference of the circle. Now, what's the other way you can get that? Take the degrees, because you know that half of a revolution in degrees is how much? 180, and multiply it by what? Pi over 180. That will convert to radians. Well, that's so easy. What happens to the 180s here? They cross out, and you get, of course, what? Pi. Yeah. So there we are. So we can think about it visually, but you can also now use these two equations. 1 degree is pi over 180 radians. 1 radian is 180 over pi degrees. What about a fourth of a revolution? Then that should be pretty easy, right? So there's a fourth of a revolution. So in radians, the length of this arc is the size of that angle. Length of this arc is the size of that angle, but that's fourth of an entire circumference, right? The entire circumference was 2 pi, correct? So you take 2 pi and then take a fourth of that, and you get what? Pi over 2? So this angle theta is pi over 2 radians. Obviously, what's that in degrees, though? That's a right angle, isn't it? Which is always 90 degrees, okay? So pi over 2 radians is 90 degrees. Wow, that's something to commit to memory immediately. 90 degrees, a right angle is pi over 2 radians. All right, let's see let's see if we can. All right, so now I've drawn theta in a negative direction. It's 3/4 of a revolution. Okay, let's now do this. Let's do this from degrees, okay? Because I think we can do this faster from degrees rather than thinking about the length of this arc. That's what we're actually computing here, is the length of this arc. That's going to be the radian measure of this angle. But we can do this really quickly, I think, with degrees. Because what is that angle in degrees? Let's see, it's negative 90, negative 180, negative what? Negative 270, right? Because you went 90 degrees in the negative direction 3 times, right? So it's negative 90, negative 180, negative 270. Oh, so theta is negative 270 degrees. And how can I convert that to radians? Really easy. How do we convert degrees to radians? What? Pi over 180. Yeah, you multiply by pi over 180. Yeah, isn't it minus 3 pi over 2? 270 over 180 reduces to 3/2. Okay, and then the pi gets left in. So you have minus 3 pi over 2. Let's see, does that make sense to us? Let's see. So if remember in radians, when you go 90 degrees, that's how much? What did we say just earlier? Pi over 2, right? So you went pi over 2, pi over 2, pi over 2 3 times in the negative direction. So that's minus 3 pi over 2, right? What about 2 negative revolutions? There's a picture of that angle. So I went 1 negative revolution, 2 negative revolutions. Yeah, you can have angles that are bigger than 1 revolution. Okay, so in calculus, angles can be any size. Multiple revolutions like this. So how many would that be? Let's see. When we go 1 revolution, that's how many radians? Do you recall? 1 full revolution. That's 2 pi. Yeah. So 1 revolution is 2 pi. So 1 revolution was 2 pi. So 2 revolutions is what? Or no? 4 pi, right? Yeah. Okay. We went 2 pi and then another 2 pi. That's 4 pi. But in the negative direction. Y'all want to do that from angles? How many from degrees? How many degrees is this? So one revolution is how many degrees? And then another is 720. So you could also think of it as taking negative. You could also think of it as taking negative 720. Whoops. So you could also think of this as taking negative 720 degrees and multiplying by what? Pi over 180. Well, 180 happens to go into 720 4 times. So you end up with just what we thought, minus pi. So here are the formulas. So here are the important formulas summarized that we just talked about. So if you want to convert degrees to radians, multiply by pi over 180. Just as easy as that. And then to convert radians to degrees, multiply by 180 over pi, just the reciprocal. Now, let me give you a shortcut for remembering which of these things to use, right? Okay. Remembering to multiply by pi over 180 or 180 over pi, all right? If you have, remember, radian measure often involves what famous quantity? I'm pointing at it, right, yeah. Radian measure often involves pi, all right, okay? Because the circumference of a circle involves pi, right? All right, so if you're trying to convert degrees to radians, you need to introduce the pi, okay? Because degrees do not usually involve pi, right? So to introduce the pi into the measurement, multiply by pi over. Now, on the other hand, we said radians often have a pi, right? Okay. If you wanted to convert degrees, you want to get rid of the pi, right? Because degree measure does not usually have pi in it. So multiply instead by 180 over pi, because the pi will divide out then, and you will have a measure that doesn't involve pi. Does that make sense to you, Amanda? That's just a device to help you remember which of these things you're going to multiply. Okay. So if you have degrees and you want to multiply and you want to convert to radians, oh, I've got to introduce a pi. So I multiply by pi over 180. If I've got radians, oh, that darn thing has a pi in it. I want to convert to degrees to get rid of the pi. It's such an annoying constant, right? So multiply by 180 over pi, and the pi will divide out. Be left with measurement that doesn't include pi, which degrees normally do not have measurement pi in it. Okay, or the constant pi in them. All right, these we can do now really quick. All right, so we can do these very quickly. These are just going to be arithmetic. So in your homework about angle measure, you're going to have lots of problems like this. They go really fast. So let's convert either to from degrees to radians or radians to degrees. So if you're converting degrees to radians, the measure is going to have the degree symbol in it, right? But if you see a measure without the degree symbol, you assume it's radians, all right? Assume radians, okay? All right, so how do we convert this? Multiply by what? Right. And again, the reason you remember that is I've got degrees, I want radians. Radians frequently have pi, right? So I multiply by pi 100 over 180, so I'll introduce that constant pi into my measure. What's 60 over 180 though? Isn't that 3? So you end up with, there's your big lesson there. First important thing to remember, 60 degrees, that's an angle we frequently encounter in practice. That's called a special angle. It's pi over 3. So 60 degrees is pi over 3. 90 degrees was pi over what? 2, right. Okay. 90 degrees was pi over 2. 60 degrees, pi over 3. Okay. What about 45 degrees? Is that next year? Oh, no. Let's do that. So 45 degrees is going to be what? Multiply by 180 over pi again. How many times? Pi over 4. So there's something else you want to remember. 45 degrees, pi over 4. 45 degrees is pi over 4. What now? What is interchangeable? The measures? 3, yeah, they're interchangeable. That's right. Yeah. Okay. And they're interchangeable in your mind. So, so it's perfectly okay if you see pi over 3 radians to think, oh yeah, that's 60 degrees. It's perfectly okay to think that, okay? Because it's very difficult to think in radians, but it's much easier to think in degrees, all right? 30 degrees is another special angle. That's one we encounter frequently. So what is that in radians? Pi over 6, right? If you can remember 60, 45, 30, and 90, then, well, it's not if you can, you must, okay? Because those angles we deal with frequently, and you're going to have to remember quickly their radian measure, right? So 60 is pi over 3, 45 pi over 4, 30 is, it's not pi over 5, it's pi over 6, all right? 0 is 0, right? 0 degrees is 0 radians, so that's nice. And 90 degrees is pi over 2 radians. So y'all convert these two for me. Well, this one we've already done easily, right? Okay. So what's minus 120? Convert that to radians. Pi over 4, that's already in radians. Yeah, so we already knew that was 45 degrees. What's this in radians? See what's the other one I've got here. Ah, so there's a nice one. So try converting these to 120 degrees, so that we would convert to radians. This is not degrees because I don't have a unit of measure here, so that must be by default radians. What is that in degrees? Okay. So you at home try to also convert B and D here. C we already know. That's one we're going to memorize. The minus sign is kind of meaningless. Just make sure you keep it at the end. It would only be important if you had to say, draw this angle. That's not an instruction here. Okay, so what about minus 120? What does that look like in radians? Yeah, multiply it by, what is it? 100 pi over 180, right? So you'll introduce the pi into the measurement, and then you just have to worry about reducing 120 over 180, and y'all told me that's the same as 2 over 3. So we have minus 2 pi over 3. Okay. If we do draw a picture of this one, let's draw a little quick picture of this one, just for reference. So we're going in the negative direction, right? So that means we'll go this way. If we get this far, how many degrees is that? That's negative 90. So we want to go to negative 120. So that means we want to go 30 more, right? So we just go a little bit into the third quadrant, correct? So about maybe there, just roughly. All right, so there is our angle minus 120 degrees would look something like this. Actually, put an arrow here too, just to indicate going in this direction from the x-axis back to this line. All right, what about D now? So I want to convert that one to degrees. That one's really hard to draw without converting it to degrees if we were sketching a picture of that. So what is that in degrees? What do we do there? Right, so you've got the pi in the angle measure, right? And when we convert to degrees, we're probably not going to have a pi in there, right? So you multiply by 180 over pi, that will divide the pi out. So the pi's divide out nicely, and then you have to reduce the numbers. Let's see, 3 goes into 180 60 times, then times 5 would be 300. So is this minus 300 degrees? There you go. So minus 300 degrees. What does that look like? Draw that, sketch that quickly. So again, we're moving in the negative direction. So let's go. Let's see. That is 90, right? And then this is 180. And then here we're to 270. That's almost to the 300, right? But we're just missing 30. So we would just go a little bit into the first quadrant. 30 degrees into the first quadrant, and that would bring us about right there, right? So here is what minus 300 degrees looks like, which is the same as minus 5 pi over 3 in radians, okay? All right, well, I mean, conceptually, that's it. But we do need to practice, okay? Because it takes a while to get comfortable with radian measure, and you do have to switch back and forth a lot. But again, don't worry about relying on the crutch of, let me think about this in degrees, okay? Because there's no doubt that the degrees is more intuitive than the radians, okay? So we move back and forth between them all the time, all right? Mathematicians too, okay? All right, so let's quit there for today, and then we'll resume with this, and next time to show where we're going, okay? We're talking about angle measures because we're going to have, again, angles and triangles, right triangles. What we're really after here is understanding right triangles. Okay. Yes. Okay, guys, at home, I will see you next time. I'm going to stop recording now.